Hi, and welcome to Banana Bites. I'm Trevani, and with me is Chris and Corey. And together, we're sort of the Banana Data podcast team, fun time gang. We are actually a podcast, Banana Data Podcast, which can be found anywhere you listen to podcasts. So please feel free to subscribe. But right now, we are doing our bi-weekly Banana Bite, which is just like a little bite of fun data science, ML, AI discussion. And so I'm going to turn it over to Corey to kick us off.
Thanks, Trevani. So today's subject will be how much math do you need for data science? Math, my greatest enemy. We're going to be talking about it today. If you guys have any questions, please feel free to ask them. We'll be happy to answer them towards the end of this. Please, we encourage you to ask. Also, if you are more interested in the subject, this is based off of a Towards Data Science piece that recently came out. So we encourage you to see that as well, just to get a little more context. So I'll kick things off. I'll ask Chris, sort of what were your first impressions of this piece about how much math you actually need to know for data science?
Yeah, that's a great question. And maybe I have a little bit of a hot take on this one, but I really don't think that you need to know a lot of math to be a good data scientist. And I'll preface this by saying that I think studying math and doing these proofs and understanding the underlying algorithm itself can only provide you value, but I don't think it's 100% necessary to be a good data scientist. Day to day, the average data scientist really just adds, subtracts, multiplies, and divides. But what you really need to be a good data scientist is the critical thinking associated with what you're doing. So an understanding of the algorithm, maybe not necessarily mathematically, but what is it doing? When does it perform well? When does it not perform well? And what do you do with the output? And where do you glean the insights? And how do you communicate that? I think is the critical thinking skills that is necessary to be a good data scientist.
Yeah, I would agree. I think the reason we're having this conversation is because of the way the field has hyped itself up into gatekeeping, frankly. Because if you think about it as a data scientist, okay, if you're writing your own custom algorithms, if you're writing your own, neural networks and all these things, yeah, you need to understand underlying math. Cool. But the average data scientist who's going to run like a random forest or even a logistic regression is not going to code that up from scratch, right? You don't need to know how to do the matrices and the matrix algebra for a linear regression. You just need to know, hey, Python, I'm going to use sklearn. Hey, R, I'm going to use the caret package. Oh, I have this other tool I can use to build my model. And it's less important to know how to get there from scratch than it is how to interpret the outcomes of that. And I think so much of the hype around you need to know calculus and derivatives and this and this and this is coming from maybe the more software engineering, ML engineer type of roles where they expect you in your interview process, at least, to know those things, even though you might not actually be using them in your day-to-day.
Well, it's interesting that you relate this to code because, as the joke goes, the best code to learn is the Google search bar. If you don't know the code, you could probably find a version of it on Google to work with. So is it similar to math? I mean, do you really need to know foundational aspects of math? Can you get by with an online calculator, graphing calculator that I still have for some reason, and just searching for an example and applying it?
Well, okay, so I think we should clarify the difference here between what we're saying about math and other things, right? Do you need to know how to take the derivative of something? I hope not, because I certainly don't remember how to do that, and I'm a data scientist. But do I need to know the underlying principles of what's happening when I run a certain algorithm, when I do a random forest, when I do something? Yeah. I don't need to know, how to do that by hand from the beginning, but I do need to understand, okay, in a random forest, we're randomly selecting a subset of the features, and then we're going to try and do some predictions based on each random subset and create this forest or whatever it might be. Or a linear regression, a logistic regression is looking for the variables, the variance, and how that variance affects an outcome using this equation. So that mathematics, and I know that those explanations were very, very, very
high level.
Chris is giving me a slight side eye right now. But I think that like that kind of high level understanding is the kind of math skills you need, less so than, okay, I can do matrix algebra.
Mm-hmm. I think code is more like, I make an analogy with code to like Legos, right? You can learn all the foundations. You can have like the yellow bricks, the blue bricks, the green bricks, and so on and so forth. And those could be like different subtopics of coding, like writing for loops or writing an object or, implementing a function and, all those types of things. But to build the castle that's on the box, that's it's the way in which you organize all those fundamentals. And you could always buy new kits and get new blocks, but if you only know each of those pieces separately, then you're not really the greatest data scientist or the greatest like Lego builder. It's what you do with those pieces that makes you a good data scientist. So that could be with coding languages, that could be with the math and statistics fundamentals. But the analogy is pretty consistent. The way in which you organize and put them together in new and unique ways is what brings your value to the table.
For all the mathematicians out there who may disagree with some of the points that we're making, I remind you, please ask any questions you may have, and we will answer them towards the end. And put any hot takes or disagreements you may have. So with this industry that's ever changing, if I could give you guys a time machine and have you go back anywhere that maybe you started getting interested in the concept or the field of data science, whether that was maybe the end of high school, maybe the end of undergrad, maybe the end of postgrad, maybe in your doctorate or in your last job or something like that, what would you tell yourself then that would apply and be more helpful now? Like, what would you focus on less or more? What would you drop and take on? Like, what would you tell yourself then so you can help yourself now?
Mm-hmm. I think it's more important to have good adaptability because, when you're in school, whether it's a math test or a data science, whatever, you're going to have like textbook answers most of the times. And there's usually a right answer and usually a wrong answer. But in the real world, there's so much ambiguity and you need to be able to adapt. So that's kind of an overarching kind of guideline that I would give out to anybody aspiring to be a data scientist is be able to think on your feet. And also, of course, think critically, like we talked about before.
Yeah. I mean, if I could go back in time, Corey, oh my God, the things I would tell myself. But
any fashion advice?
Not even fashion advice, beyond that, right? Like, remember that guy? No. Anyway. So I think from a data science perspective, I actually got into data science sometime at the end of my doctorate. And because if you had told me this in high school, I would have been like, what are you talking about? Who cares? And it was not till the end of my doctorate that I realized, okay, I need to like actually pay attention to this thing. And I realize now, looking back from that time, which was only 4 years ago, to here, I wish I had spent more time focusing on the sort of interpretation or the use of what I'm doing. Right. Because I can go ahead and build out a fancy algorithm and build out this like amazing, like beautiful, pipeline to process my data and put it through the data science pipeline. But what am I doing with it at the end? Right. And part of that means asking the right question up front. Because if I do this whole pipeline and I get to the very end and I can't tell you why it matters or like what you can do with this information that I've now created, then I probably didn't even ask a good question at the beginning. Mm-hmm. And so it kind of is like the critical thinking question or critical thinking argument, but more so than that, like knowing how to ask the right questions or at the end of your process, be able to say, okay, here's what I can do with this.
Mm-hmm. Or like, what's the bottom line? Why does this matter? Why would people care?
Yeah.
It's like telling that story arc, if I'm understanding you correctly.
That's actually good advice for me in high school. Like, why do you care?
Well, the most important math problem I learned in high school was in Mean Girls, where the limit does not exist.
Oh, God. Yes.
You got the bottom line. You guys sound like such business people. It's really, it's wonderful. You should be proud. since you are such experts in critical thinking and understanding the bottom line, what in the future, like, is there anything that we think in the future that's just going to be like, nah, we don't need this, forget it, just drop everything you're doing right now and stop doing it? Or, I mean, are things going to stay foundational, or are things going to, are things rapidly changing or becoming more obsolete?
Chris, I need
I can
to think through.
Yeah, that's okay.
Yeah.
That's a good question. And maybe I'll flip it on its head a little bit. I think what will stay the same is something that we can claim, at least I'll make a claim for that. And then, talk a little bit about the adaptability piece. But the foundations of regression and classification and reinforcement learning and adaptive learning and those broad buckets and umbrella terms, I think will stay the same. So having an understanding of when you might use a regression versus a classification or something like that, I think is necessary. And of course, the baseline foundations of like logistic regression, linear regression, stuff that is usually like the basics that get you into the field. What will change is underneath each of those buckets, there may be a brand new algorithm that somebody writes and it's great at predicting and so on and so forth. That is the adaptability piece where you have to be able to, parse that information and kind of understand what this new algorithm is doing, and be able to maybe work that into to use an analogy from earlier, work those pieces into your Lego blocks moving forward. So I'll make a claim to what stays the same, learn those basics, foundations, and umbrella categories, and be willing to, pick up new things on the fly.
Yeah. I think we should buy Chris Legos for Christmas.
He's definitely sending signals.
He's sending big signals here.
Yeah.
I think that for me, what's going to be important in the future is, again, less of like I can do this like super crazy fancy thing, and more of here's how what we're doing is impacting people in real life. And the sort of ethical, responsible AI element is going to be huge moving forward. So if you can get your foundations right so that you can say, here's how this model made this decision, and then use your critical thinking to say, here's why that decision might be really bad for other people or might not be the right choice for what we want to do, then you're going to, if you can develop those skills, you can really set yourself up for success in the future. And so I think like focusing more on how what we do matters outside of the code, outside of the math, is going to be a really important skill.
Looks like we have one question. So what are your views about the advanced statistics concepts? How much of it is necessary? I think it is important to at least know what it means. What means what in statistics, isn't it?
I mean, yeah, obviously. And I think Chris, as like stats man, would definitely agree. You need to know those fundamentals. Like, otherwise you can't understand the data. But do you need to know how to like derive those from scratch, from like prove the theorems? Probably not.
Mm-hmm. Yeah, I agree. I think, just for a quick answer here, for a chi-squared test, let's say, I need to know why I might use this test and when it's appropriate to use this test, and understand, how to code it up and get an answer and interpret that answer. But I don't necessarily need to know like what, the distribution and all the things about the degrees of freedom and all those nitty gritty elements, just to know that I'm using it appropriately and in the right context.
Right. And especially because so many tools exist now to help you do those things, right? Like I don't need to have the T student distribution memorized because I can just look it up, or I can just like go to Dataiku and like plug it in and use the chi-squared fact. Yeah.
Thank you for your question, Vinay. Do you guys want to hear my favorite equation?
Oh my God,
yes,
yeah.
Please.
If you guys like this content, plus hitting the subscribe button equals more opportunities to provide content from the Banana Data Podcast. So I think we could probably end it on that.
I think we should end it on that. Thanks everyone for your time. And as Corey said, please check us out on wherever you listen to podcasts. And we'll see you again in 2 weeks for our next Byte.
Bye.
Bye.